Hello guys, welcome to this series which is on machine learning fundamentals. We were on a very important topic which was related to in fact core machine learning algorithms. In this category we'll be discussing in fact those algorithms that are relying on proximity matrix. So KNN, naive Bayes, SVM and others which are there. They will be coming under discussion in this particular category. We had discussed, in fact, first part of the this episode, which is probably episode 15 of the series. So first part of this we had discussed, and in that it was very short, in fact, a short video of 10-11 minutes. And that is discussing in fact the foundational concepts where we are talking about what is distance metric, which forms in fact the foundation for understanding all of these algorithms that I was talking about. So let me just give display this presentation. This is core machine learning algorithms. We had discussed in fact last episode what is distance metric, and then related things which are to this, and why it is important to machine learning, especially those algorithms that are relying on proximity metrics. And then we visualized it. We provide example which is on in fact the student performance. That example we had been taken for for we have taken it for understanding different algorithms, and in fact it is the basics that we are giving actually to understand the algorithm, and then we are going on to take complex examples and understand things at an advanced level. So today, in this particular part, second part of this episode, I would like to discuss first of all common distance matrix. So we had in fact talked about this a little bit earlier. So for in fact common distance metric which are used in fact in machine learning, Euclidean distance is one, Manhattan distance is one more. Then we are having Minkowski distance, and then cosine similarities one more. So we are going to actually dissect them and understand them one by one in a complete manner. So if we are talking about Euclidean and Manhattan distances, and these are the visual representation which is in front of you now, you can just see as far as Euclidean distance is concerned, the straight line path between 2 points, ideal for continuous spaces where direct measurements matter. So definitely the direct measurement matters in these kinds of situations. So this Euclidean distance can be calculated between 2 points, where normally you are having a straight path between point A and point B, and then definitely it is ideal for continuous spaces where direct measurement matters. That is something significant, and such as geometric calculations. So this can be used for, so examples are there where Euclidean matrix can be used. It can be used for geometric calculations and spatial analysis. So these are the areas in which these calculations do matter, and they can be taken into consideration. In comparison to this, if we see Manhattan distance, it's a grid-like moment along axes, and it is in fact best suited for discrete spaces. So it is not a continuous space; it's a discrete space. For example, steam navigation can be an example where things can move in different directions. So it is not a straightforward path, or a distance from between point A and point B. So steam navigation can be a very good example, and Manhattan distance is in fact used to in fact calculate distances like that, or when diagonal moment isn't possible. So you don't have diagonal moments possible. So if you just see the line which you can see on the graph with the blue color, that is a Euclidean distance. Yeah, so if you just see one more line which is with orange, that is Manhattan distance. So definitely like walking on the steel blocks can be Manhattan. It is not a open space, or you can just say a straight path, continuous space where we can have distance calculated from point A to point B. So Manhattan distance, normally it is used for these use cases, or you can just say application areas like steam navigation, or walking between between steep blocks. So this can be used there. So one is Euclidean, one is Manhattan. I hope that you have understood the difference. While as these two, if we just see Manhattan and Euclidean distance, we can have the unification of both of them. We know that one is used when there is a continuous space and diagonal moment is possible, and one more is used where you don't have such a mechanism, for example navigating a ST or walking through different blocks. That cannot be a straight path. So but we can have a unification of these two, and when we are having unification of Manhattan and Euclidean distances, we're getting something called as Minkowski. So and cosine similarity, in fact. So cosine similarity and Minkowski distance. If you see, Minkowski distance is a generalized distance metric that unifies Manhattan and Euclidean distances. So this is used, it represents the unification of two types of these distances which we have already taken, Euclidean and Manhattan. So it is giving as an example when we are saying that P is equal to 1, P is equivalent to 1. It is, for example, Manhattan distance. When P equals 2, it becomes Euclidean distance. The flexibility allows you to tune the metric based on your data characteristics. So definitely when it comes to Minkowski distance, it gives us flexibility so that we can use it for a wide variety of problems. So that flexibility allows us to tune the metric based on the data characterization, what kind of data we are having, which particular application of that. And then we are having flexibility that we are unifying these two distances and we are having one thing. So cosine similarity measures the angle between two vectors, focusing on direction rather than magnitude. So if we just see cosine similarity, it is measuring angle between two vectors, and definitely it is focusing on direction rather than on magnitude. It's particularly powerful for text and document similarity in NLP. So this is one of the major areas in which it can be used, where word frequency vectors may differ in scale but share similar orientations. Of course, this is not the only problem, but this is one of the major problems where we can just utilize this particular cosine similarity. So definitely these different kinds which are there, the common, if you just see common distance matrix, we have discussed all of these: Euclidean distance, Manhattan distance, very simple to understand. There's a unification of the two which is called as Minkowski, and there can be application areas in which we would like to have flexibility, and then we will be opting for depending upon the characteristics of the data. And then in fact cosine following it, we have seen that a cosine similarity measures the angle between the two vectors. So definitely it focuses more on direction, because when we are talking about it focuses more on direction rather than magnitude. It is particularly powerful for text and document similarity in NLP. So you can just see it is establishing similarity, text and document similarities, for example in NLP, natural language processing, and where word frequency vectors may differ in scale, but they share similar orientations. So frequency vectors may differ, but they are sharing the similar orientations. So that is something which is, and this kind of situation or a scenario can be somewhere else apart from NLP. If you just see this Python demonstration, which is in fact calculating a distance matrix. So we are using, in fact, Euclidean, Manhattan, and Minkowski. As far as cosine similarity, we are calculating all of these. We are having a situation where a student's grades, in fact, are given. Two students, in fact, 2 points are there, and we have to calculate these distances. One student is having, for example, study hours as 4, and the attendance as 70. One more student B, so this is about A, 4 and 70. One more student is having this study hours of 6, and the attendance is 80. So if you just see these 2 points separately, we have to calculate the distance between them. So we will be having Euclidean distance, Manhattan distance, Minkowski, and then cosine similarity. And results will be showing different, matrix capture, distinct aspects of particular relationships. So with those, then interpretations are coming into picture. Let me first of all go directly into this program which is there, which is in fact talking about this, taken into this. I'll be giving you an explanation of this, complete explanation. So first of all, we are importing the libraries that are required for this particular example. So NumPy is something which will be important because we are plotting. So matplotlib will be important, and then in fact the distances, when it comes to calculation of distances, SkyPy pi is in fact something useful, wherefrom we are importing these functions which are Euclidean, steep block, Minkowski, and cosine. So these are different kinds of you know calculations, distance calculations, that will be taken into consideration in this particular program. So then we are putting the calculation distances. Euclidean distance is this, from point A to point B, and then Manhattan distance is steep block, that is represented by steep block in the SkyPy. So steep block, point A to point B, that is what we give as an example as well. When it comes to Manhattan, it is not a straight open space. It is in fact something navigating in a steep block, or having a navigation. So then Minkowski distance is Minkowski point A, point B. So P is equal to 3. I'll be talking about this. And then cosine distance is equal to cosine point A, point B. So you can just see, it is giving these different, calculations first of all, and putting them in these variables. And then what we are saying is, it is first of all printing point A, then it prints point B, and then it is printing the distance, for example Euclidean distance, and it is putting then the Manhattan distance, and it is putting in fact the Minkowski distance, and then cosine distance. So all of these are printed, and then in fact we are getting the figures, the plot which is there. First of all, we are saying that it has to be 8 by 6. So this is height into width of a plot figure which we are printing now, which we need to output. And then we are saying that you put a scatter, so it will be putting a graph on one side, then it will be putting the points first of all of x-axis, that one side of it. So point 0 and point 1, the distance label point A, and that S will be 120, means the point which is measured there, or which will be printed there. What will be, how significant it's going to be. 120 is going to show us a big point. So then it is plotting one more, which is a point B. Again, it will be calculating between distance between 0 and 1, and point B will be there, and it is 120 again. And then this particular line which is there, it will be printing this, and then we'll be having one side X label as study hours, Y label will be attendance, and then title of this graph will be distance between two data points. And then these things, in fact, plot.should is putting that, and grid lines are given there. It will be putting legends as well. So grid and legends are there, that is going to print. So this whole code which is here, this is for plotting. In fact, this is printing here, and I show you the output of this. Let me just go to this output, and I'll be showing you the output. I say run, and run this. First of all, let me just take it a little up from here, so that it is displayed in a proper manner. And I go to run, and I say run this without debugging. First of all, it should be giving me the point A and point B. So point A, it is putting 470, which we had given, one student's study hours, and then the attendance. And point B is 6 and 80. So one more student's study hours and the attendance. And the Euclidean distance, if we are calculating between these two, that is coming to be 10.2. And if we see Manhattan distance is 12, and then Minkowski distance is coming is equal to P3. On P3 it's coming as 10.03. We'll just clarify this, so this is going to be clarified in the next example. And then cosine distance, which is 0.0002. So definitely, if you just see that these 2 points, if we have to see that how dissimilar they are, um, you know um, because cosine distance will be calculating how dissimilar, because when we are saying cosine similarity, it will be giving us how similar these 2 points are. So they are 0.98% similar, so it's almost 1 is the maximum value, so they are almost similar, these two are almost similar. And then the results which we can calculate, because if we are having results near to them or falling between these 2 points, so that will be again the same. So we are just calculating the distance. We are not putting anything or applying any algorithm to predict any new students, but we are just calculating the distance between the two. And here is the graph which is there, which we have plotted. If you just see, it's exactly the same, how we have done it. Distance between two data points is the title which is coming, so that we had given here. I'll just show it to you, one moment. So this is where we are giving the title, so distance, so plot title is here. I'll just display this result again. See, this is the plot title. We are having x-axis as x label as study hours, which is coming from here, and y label is as attendance percentage. These two are representing that. And then these points which are there, so when we are putting point A0 and point A1, that means we are putting this, it is putting a mark there, and then that particular thing. So here, if you just see plot this, so this is saying that point A0 and point A1. So this will be putting both of these points, both of these aspects it will be taking into consideration, which will be in fact the attendance and the study hours, and on that it will be marking. So if you just see, it is 4 and 70 here, so it has marked first point here, which is point A, and then it is 6 and 6 is here, and then it is 85 like this on the other side. So it is 6 and 80 from other side, so it has marked one more point here. So if you just see, these are marked exactly at the same level what we are mentioning. So these are actually plotting them. And then this point which is here, it will, you will understand it better. The point, the area of this point, how big it is, that is, s equal to 120. So if you decrease this value, this point will become smaller. So that is how it comes. So we can just see that as well. If I just close this, I can just reduce this particular point. One moment. So I will reduce it. So let me just keep it 60, one of those 60, and one more I can just keep again 60. So we'll see how much reduction will be there as far as these points are concerned. So that is there. Let me clear this. Although this is not going to have any difference on the results, but it is just for the sake of understanding, so that you understand the plot. Actually, you should be having this understanding already. So if you just see, we have reduced it to some extent, in fact. So one moment, I will be just displaying these points there. So it is label point A and point B, so that is there, and this is giving us 160 and 60. So that should be, in fact, if you just see this, it has resulted in little bit of a change, not a major change, but because this is in these points which are given there, so that will be making this different. But we can have this as a significant difference as well. So this is making a change. So let us just, for example, take it 250. So 250, and we can take it 250. So we can just check the results on this as well. If we are having this, just put it again, and just see that how this is going. So if you just see now, it's a significant, difference which you can feel. So you just see these 2 points are very big. So this is just for the sake of understanding, so that you understand these values which have been put. So this, because some of the viewers, they might be getting confused, although I have discussed this in certain series. Some of the viewers, they are taking actually these things. If somebody has to directly go to, for example, these concepts which are discussed here, because these plots and all, I have explained those in previous series to certain extent. Although these are not actually the core part of the algorithm itself. This has to do with the basic Python capability of a particular person. But just for the sake of understanding, so these things which are here, so these lines which are here, we are putting actually these points from which are taking into consideration two things. One is study hours, and then second one, point A, it is putting study hours and the attendance. Point B again is putting study hours and the attendance, and it is plotting them. And we are putting 250 here, so that we can just see how big the point is. So we can make it less or small depending upon how we want to get this thing done. So that is there. So that we'll be able to see this, and then this plot is putting the Euclidean line. So it can be different, but we are putting Euclidean, a straight line which is there, and that is giving us the result. And this is distance between the 2 points. Coming back to our topic of discussion, which is after this, which we had in fact we were discussing in fact the one moment, I'll just go back. I think something I was not able to actually display the slide which was there. So in fact this is the wrong one. One moment. So it is this particular slide, which is okay. This is the one. So this is the one which we were in fact discussing. This is a Python demo which I have provided. And what is instance-based learning? So now this is something which we will be in fact going to this, and then maybe one example on KNN, and then we'll just wrap it. So stores training data. What is instant-based learning? It stores training data. The model retains all training examples in memory rather than building an abstract representation or formula from them. We had seen earlier, many models, they are actually learning. When we are talking about, these this instance-based learning, so this is happening in a different way compared to what we had seen in a decision tree classifier or random forest. So there it is actually learning the patterns, and then it is able to predict based on that. That is a real learning which happens in those models. But here it is different. It is little different. It stores the training data. So training data is directly stored. So there we had said that this is not matching actually. But here it is different. It is storing the training data. And then the model retains all training examples in memory rather than building its an abstract a representation or a formula from them. So it is not doing that. It is retaining all the data which is there, training data. No explicit formulas are there. Unlike parametric models, there are no mathematical functions learned during training. Predictions are based are made at a query that is made. So query time dynamically, when the query is in fact initiated, then the predictions are in fact done. So that is one thing. And it is learning by remembering. So these kinds of models, they are learning by remembering. There are no predictions made by comparing input to the stored examples and the findings, the most similar instances. No. So new predictions are made by comparing inputs to the stored examples and findings, the most similar instances which are there. That's why we are calculating the distances. You will come to know. Instance-based learning example, it is giving an example like this. Training data, student A, 5 hours of study and 75% of attendance. It is given as a pass. Student B is having 2 hours of study hours and then 50% of attendance. It is given as fail. Student C is having 6 hours of study hours and 85% of attendance. It's again pass. And student D is having 3 hours of study and 60% of attendance. Percentage of attendance is 60. It is fail. So now if we are giving a new instance of a student where a student has studied for 7 hours and percentage of attendance is 80, for example, by comparing to stored examples, the closest neighbors are student A and C. So both are pass. Student, if we see the closest neighbors of 7 and 80%, new student who is having study hours of 7 and attendance percentage of 80, who are the closest neighbors to this? We will find that two closest neighbors to this student are student A and student C. And KNN is predicting that both pass based on majority vote of the nearest neighbors. This particular student is passing because both of those are passing, and then we are having the closest neighbors first of all, and then we'll be having, in fact, the vote of nearest neighbors. And when we see vote out of these two neighbors who are there, both of them are passing. We are predicting that this student is also passed based on KNN. K nearest neighbors, KNN algorithm overview. KNN predicts by finding the K closest training examples to new data. So it is finding K. So K will be, for example, equivalent to 2. It will be seeing that, how many, these three closest neighbors who are there, and it will be voting amongst them. We'll say K is equal to 2. It will be taking into consideration two closest neighbors of this, algorithm, of the value, and then from there it will be predicting the value for the next one. So these are data points using majority voting amongst their labels to determine the prediction. That is number one. And distance metric, Euclidean Manhattan distances are essential for identifying which neighbors are nearest to the input data point. Okay, that's right. And simple prediction flow is there: input new data, calculation distances, finding the k nearest neighbors, and vote on labels. So majority vote will be in fact prevailing, and then that will be given as an output. So output predicted class. Now this is how it happens. If you just see applications, we are going to take example on this. I'm having a program, I'll be just putting it in front of you. There's nothing new in that, just KNN model has been implemented. The points, the distance between 2 points, we have already done it now, and it will be based on that, and then you will see the KNN has been implemented. Very simple program which will be giving us output for a new value. So KNN excels in classification tasks such as image recognition. So this KNN is very useful, and it excels in such certain applications, like for example image recognition is there, handwriting direct detection, recommendation systems. Its key advantages include simplicity, no training phase required, and effectiveness with small to medium data sets. And considerations are there. KNN can be computationally expensive. Definitely, it will be with large data sets and is sensitive to irrelevant features. So if irrelevant features are there, it is very sensitive. It can give some bad results. So tips for success: choose an odd k value. That means so that deciding factor will be there. For example, there are three neighbors. If two are saying pass and one is saying fail, it will be going the two. So that is because sometimes if you are having four neighbors, so two can say pass and two can say fail. So that is going to be a problematic thing. So to avoid ties, scale your feature for fair distance calculations and use cross validation to find optimal k. So these kinds of things can be used. And let me just go without any further delay to this KNN classification, where one more program is there, and you can just see we are putting the study hours and attendance and results for this data is there. And we are not doing anything new. X and Y, you are already aware about this, we have done it before. And we are putting this simply data set, then X and Y, and we are using 25% for the test. And then we are using the k neighbors classifier in this. So it is here, create a KNN model, and then we are training the model. So this is what we are doing, and this is not something new. We have done it prior as well. And then we are printing the results here. If you just see confusion matrix, we are having a classification report, and then new student is, for example, 6.5 and 75, how it will be predicting that, and new student whether it will be pass or fail. And then we are plotting a graph on this. It will be plotting on the graph on the previous two and the new student which is there. So if you just see, I'll just run it. uh, so this is the result. It should be now there. So what it is giving us, first of all, it will be giving confusion matrix, which, see this one. So confusion matrix is here. It has predicted in a correct manner. So if you just see, accuracy is 100%, and then recall F1 score in this particular case is 100, and then you can just see new student prediction is pass, and it is giving some other factors which we have discussed, in fact, a lot of times before. And then with the graph, what we are doing, actually we are printing fails with the blue. You can just see that from the code there. I have already explained that. And pass, it is putting with the this orange color. And green, we are using a different, it's using a star. I can just show you there as well. It's using a star for that. So it predicts it because it finds that two neighbors, which are there, three neighbors in fact, of because we are using three neighbors here, nearest neighbors of the new value, they are all passing. So it is predicting this particular case as pass. And then it is putting this, if you see Euclidean, this one is there, and then attendance from this side, and these are study hours. We were having 40, and one more example which was there, that was 85, 6 and 85. So that was this one, somewhere here, maybe, yeah, this is the one, or this is the one. And then we are having one which is coming as 7, so which is here. So 7 and 80, so that is somewhere here. So you can just see these, the new example, it is 6.5 we are calculating on, sorry, 6.5 and 75, not 80. So that is coming somewhere here. So this is the one. And then the ones which we had in fact given, that is it is plotting them here. So these are the different points which are there. So these different points, they are here, the data which is there. If we just see, this data is in fact here, all of these. So starting with 1, and then 40, 45, 55, and then 65, 60, 65, 70, 78, 82, 88, 92, and 95. So these are the passing ones in fact which are from here, and these are the failing ones which are with the 0, and all of these are there. And then we are plotting it. If you just see the plot which is for the last one, we are saying that age 6.5 and 7.775 marker is star. So we are putting a marker as star, and s is equal to 250. So here also we are putting, I believe, the 250, or maybe lesser than that, 100 we are putting maybe. So if we see the earlier plots here, we are putting s is equal to 100 here, s is equal to 100. So this marker of 250 which is here, it will be bigger star. So that's what we are getting with a new student. I think this should be giving you the deeper understanding of how these algorithms are working, and we will be taking in fact the advanced examples in this in the coming portion of this series. This is in fact episode 15 of this series, and we'll be just discussing some other algorithms which are falling in the same category, where proximity matrix matters, and we'll be going deep into it, taking some further advanced examples for having better understanding of these algorithms. Thank you so much once again for joining. Please provide us your valuable feedback so that we can enhance this channel. This channel is just for the purpose of facilitating and helping those people who want to learn machine learning. We are living in the age of machine learning, artificial intelligence, and such kind of things with cybersecurity. So this channel is dedicated for those students, free of cost. Nothing is there, and this is actually intended for the purpose only, so that it can help for outreaching the community, and helping those students and viewers who want to just establish the understanding, better understanding, or who want to learn machine learning, artificial intelligence, or cybersecurity and related topics. So please provide us your valuable feedback so that we can enhance this channel. In fact, you can provide for this particular series and how this is beneficial for you, and you can just subscribe to the channel, so that in case a new new episode is uploaded, or any video is uploaded to this channel, you'll be getting a notification for that. Thank you so much once again for connecting, and see you on the other side.